Today I'd like to go over a principle of forge welding that I truly believe has become lost over time. Somewhere between the time when forge welding was an everyday occurrence and smiths did hundreds of welds a day to now when we're trying to figure all this stuff out again, this little bit of information has gotten dropped, and I think it's really caused a big problem. And the principle is simply this, that the full strength of a forge weld is developed over several forge welding heats. So unlike the commonly accepted theory that suggests that forge welding is a one-shot deal that really centers around that one heat that joins the two faces together, I'm suggesting that the forge welding process actually is carried on after that heat. So there's basically two steps to the process. There's the initial tack, where you're joining the two faces together, and that allows you to treat the bar as one piece of steel. And then there's the actual forge welding heats that develop the strength of the weld. And I think this process also solves the mystery of the scarf joint. The currently accepted forge welding practice allows you to work with pretty minimal scarf joints because you're only trying to run through maybe one or two welding heats, whereas historically scarf joints have always been shown to be very massive. And that stands to reason because if you plan on running a section of bar through several forge welding heats, you are going to need to take the time to make substantial scarf joints to give you enough material to run through that whole process. Now, I began working with this idea a short time ago when I discovered a process called diffusion welding. Diffusion welding is basically forge welding done in a laboratory. The pieces that are being joined are machined so they fit together perfectly. They're heated up in an oxygen-free environment. There's a specific amount of pressure that's being applied to the whole forge weld. Basically, there isn't anything left to chance. But the thing that I found interesting about diffusion welding was the length of time that the whole process took. These things are clamped together at a forge welding heat for a half an hour to an hour, depending on how complicated the forging is. So that got me thinking that if something as clinical as diffusion welding required that length of time to produce a good weld, certainly something as crude as forge welding would benefit by additional forge welding heats. So that's what I'd like to demonstrate in this video. The whole idea that if you have a good internal structure to your weld, if there's no contaminants or any mechanical things that are preventing a good weld from happening, the strength of that weld is going to improve with subsequent forge welding heats and additional hammering. To create the sample pieces, I'm going to be using a simple lap joint. I'll be creating three samples. The first one is going to have one welding heat, the second one is going to have two welding heats, and the third one is going to have three welding heats. I use regular borax as a flux, and I usually start fluxing the bar as soon as I'm done shaping the weld joint. The borax combines with the iron oxide in the scale and forms a very basic form of glass. It'll look like a thick candy coating here because the bar is relatively cold, but it turns into a very fluid glass at welding temperature, and it's continually dripping off the bar, so it's important to reapply the flux several times during the heat to protect the bar from the fire. The initial weld on this bar is a pretty standard forge weld. I'm just bringing it up to a bright yellow heat and hammering it out on the anvil. For the bars that are going to be getting a second and third welding heat, I always use flux during those heats, even though there are no exposed sections of the bar that need to be welded. In this instance, I'm using the flux as an insulator to protect the bar from scaling away in the fire. When I've completed the lap joint, I cut away the bend of the joint. So now the only thing holding the bar together is the forge weld. In order to create a cross section that I can test, I cross-peen the forge weld into a very thin flat section. This will give me a short section of flat bar with the welded seam running approximately in the middle of the flat face. And then I'll repeat this process with the other two bars. So I'll have three test pieces, one that has one forge weld, one that has two forge welds, and one that has three forge welds. So now that I have my 3 test pieces, I can place them in the vise and try to break them along that weld line. The first one that I'll be testing is the first sample with only one forge weld. And as you can see, it doesn't take much pressure to break this weld once we're able to apply pressure directly to the weld joint. The interior surfaces are clean, there's no contamination, it just didn't have time to mature into a proper weld. The second sample piece with 2 forge welds offers quite a bit more resistance. The weld is actually strong enough that I need to bend the sample before the weld will break. But like the first sample, it breaks cleanly along the weld line, and it's obvious that the welding process hasn't been completed. So even though this would be considered a very serviceable weld today, and certainly more than adequate for any decorative purpose, it's important to understand that the weld still needs more time at a welding heat to reach its maximum strength. The third sample piece is showing the completed weld. I'm able to flex the test piece back and forth until the steel starts to break at a stress point where the locking pliers were placed. The weld itself did not break. So you can see the difference that the additional forge weld made. Even though forge welding is considered a mechanical bonding of 2 surfaces, this sample is acting like one seamless piece of steel. The 2 faces have been locked together to such a degree that they are now as strong as the surrounding steel.